Science, like the Olympic Games, has its gold medals. They're called Nobel Prizes. And today, one of our gold medalists is going to trot round the course and do a lap of honour. Dennis Gabor, professor in our electrical engineering department for many years and now emeritus professor and a senior research fellow of the college, has recently delivered his Nobel Prize lecture in Stockholm, and he's going to repeat it here for us. In calling on him to speak, may I offer to him from the college our most delighted congratulations on this honour. And now, to save time, because he's got a lot of slides to show and we may not have power for very long, I'm going to ask him to give his Nobel lecture, Holography, 1948 to 1971. Professor Gabor.
Lector, ladies and gentlemen, a part cut threatens us in 20 minutes, so I have got the choice either of delivering 1/3 of my lecture or to chase the slides through one after the other and then talk in darkness. So I'll make a compromise between these two because otherwise you won't understand anything. The holography is based on the wave theory of light. And the wave theory of light is the work of that extraordinary genius Thomas Young. Who in 1801 performed one of the simplest and most wonderful experiments. Here it is. Here it is. Here he took a spirit lamp and put a pinch of cooking salt into it. Then he pierced 2 pinpricks into a little screen and put another screen before it. And then for the first time he saw man-made interferences, that's to say darkness produced by light. Now the explanation is, which you of course intuitively foresaw, that monochromatic light is a regular sine oscillation. And where wave crest falls on wave crest, there you have a maximum of light, and where a wave crest falls on a wave top, there you have extinction. Now, I must make you familiar with the idea of amplitude and phase. Amplitude means, of course, simply the height of the sine oscillation, and phase is then the relative position of 2 waves. If they coincide where they produce brightness, then they are in phase, otherwise they are in antiphase. Now, I have to jump quickly 150 years. In 1947, I was very interested in electron microscopy. And we knew that this wonderful instrument had come to a bottleneck. It could not be improved to the point when we could see atoms with it or resolve atomic lattices. Theoretically, the resolving power was limited to about 4 angstroms. Practically it wasn't even definite. So how can we get around this? The trouble was the spherical aberration of electron lenses, which could not be directly eliminated. It's impossible to make a perfect electron lens. So I started thinking how we could get around this. What about taking a bad picture and then improving it by optical methods? Because in optics you have correction methods. Yes, but if you take an ordinary picture, we don't get the whole information into it. We get only the amplitudes or intensities, but we don't get the phases. And so I said to myself, Well, that's not surprising that we lose the phases because there's nothing to compare them with. Let's put a reference wave, or as I called it at that time, a coherent background to it, and then we may be able to see the phases. Now the idea came to me in this form one nice Easter morning in 1947. That's about as I show it here. We take 2 point sources. One of them we can call the reference source. And then we simply put a photographic plate before it. Now, where the phases coincide, there will be maxima of light. Now we take a positive photograph of this, a hard one, so that it has got slits where there were maxima. And I said to myself, now if you put only the reference source behind it, we must see also the object point, because the phases are of course right for the reference wave. They are the same as the phases in the object beam, so therefore the object must also appear. This was just about the argument, and a little mathematics showed that it was correct and even much more general. In fact, it turned out later that in holography there's no need to take any half positive and any negative will do. Holography is so tolerant that you can make a very good holographic portrait, which a plate which is so hard that you could see only blacks and whites on it. Next one, please. So don't forget, considered all this only as an improvement in electron microscopy. And this was the suggestion which I made in 1947, appeared 1949. Take a hologram, that was the name I gave to this interference figure, and with electrons, and then correct it with light. Next one, please. This is one of the first holograms and its reconstruction. The apparatus was extremely simple. It was a mercury lamp, of which I took one line, green, for instance, the green line, then illuminated a very small hole of about 3 microns with it, and in front of that put a little microscopic picture, like this here. Then the hologram looked like nothing on earth, but after that, going with a microscope through this, you could see the fair reproduction of the original. So that proves the principle. Next one, please. This is a somewhat better picture. Here you can see the names of the great creators of optical theory, and then neatly translated into Arabic. Professor Salam, apologies. And then retranslated. And but of course the reproduction wasn't very perfect. Now what's the reason for that? Next one, please. The reason is that we got not one reconstruction but 2. We got a second image. The explanation is here in a simple case. Let the reference wave be a plane wave coming from a source of infinity. And then you get interference fringes from any point scatterer which have the form of Fresnel zones, alternate blacks and whites. Now it's well known that these Fresnel zone systems act like lenses. They're called Sorel lenses after the French optician who first realized them. And they have a positive and a negative focus, because obviously there's nothing to distinguish fore and aft here. If the phases are right for the original point behind it, they'll be also right for the point at the same distance in front of it. Now, at that time, there was no simple way of eliminating the second image. I used a rather complicated way. Next one, please. The idea was to improve the electron microscope, and that in itself had the advantage that the electron lens was a very bad lens. Now, if you have a bad lens and make a hologram with it, after the correction, one of the 2 images is sharpened and the other is twice as diffused as before. And so I was able to eliminate the second image fairly completely, and we went with some confidence at this work. I won't tell you now because there's no time, in the end frustrated efforts which we made at that time in the Associated Electrical Industries Research Laboratory in Aldermaston. We worked for about 3 years on this idea to find out in the end that we had started about 20 years too early. When I worked on here in Imperial College, which my student and collaborator Walter Goss produced a holographic microscope, went peddling it on in 3 countries to get the answer. Well, we make interference microscope only for prestige, and thank you very much, our losses are already covered. But then came the explosion. In January 1964, on the front page of the New York Times, which is quite a well-known place now for first publications. Next one, please. And it was the work of Leith and Upatnis of the University of Michigan, Ann Arbor, who for the first time applied the laser to it. Now there's again no time to explain which what excellent theoretical preparations Leith started, because he had done secretly, we didn't know of it, work on electromagnetic holography. So the work, but the work was enormously helped, of course, by the time they had the laser at their disposal, a source of coherent light, which even right at the beginning was about 3,000 times more coherent and several million times stronger than the mercury lamp which I used. That had the advantage that now you could make large holograms. I could make only microscopic holograms, and had to use the most sensitive plates, whereas now it was possible to use fine-grain plates, so there was an enormous progress. Now the trick which they used to eliminate the second image was a very simple one. It was made possible by the laser. I simply put the reference beam skew to the plate. This requires more coherence, but the laser could supply that. The result is that the 2 images are now not in one line as originally. The one is perfectly out of the way, and this made it possible to obtain very much better holograms. I want to mention, though, that with the laser, the old inline method which I used is also very much better. Some holograms I'm going to show you later, electricity permitting. We are taking which inline systems. Next one, please. Yes, now these are some of the 2 of the first holograms of Leith and Upatniks, and the curious feature is that these were taken in one emulsion. They're both contained in one emulsion. This was the first intimation that holography allows an enormously better utilization of photographic emulsions than ordinary photography. These 2 pictures are in the same emulsion. They don't disturb each other at all, because they were taken with different azimuths of the skew reference. Nowadays one can go and store at least 50 black and white pictures in an emulsion which otherwise would take 1. Next one, please. Yes. Now this enabled at once also to make large holograms and to take 3-dimensional holograms. Holograms were 3-dimensional right from the start, but in my microscopic holograms we had to go with a microscope through the field to see where the object was. Now with large plates one could simply look into it with 2 eyes and see the object there in 3 dimensions. In the case of diffusing objects, it's very simple, just the same arrangement as before. The diffusing object sees to it itself to distribute the information and a small part over the whole plate, so that anything the plate has seen will be visible also to the eye. Next one, please. Yes, here is a 3-dimensional picture of a statuette of Abraham Lincoln. It's illuminated from behind with a laser. The hologram itself is invisible, it has been bleached. And curiously observe that the shadow is behind the figure, though the illumination is from behind. A rather mysterious phenomenon. I have to chase through these slides very fast. Now, such a diffuse hologram, it looks like nothing on Earth. It looks like pure noise. Nevertheless, this is not noise, this is information. How is the information concealed in it? Well, it's not really as if you had thrown sand. Now here we are. If you had sand grains one on top of the other, it's rather as if you had thrown the diffraction figure of the object many times, but parallel to itself in the same size on top of one another. Now, ladies and gentlemen, you understand why I'm devoting more of my time nowadays to the interface between technology and society than to the improvement of holograms. Here we have got a breakdown of the interface. So now I have to do it with short slides, and that is of course exactly like what? This is only for 1 minute, I'm afraid. Yes, next one please, quickly. Yes, this is a reconstruction from it. As you see, it's very perfect. Next one, please. While the going is good. Yes, this is the sort of standard holographic equipment which is now used in hundreds of laboratories. Consists of a very solid granite plate, very heavy, sometimes several tons, and on top of it is built up a laser and all this photographic equipment. Nowadays one can get such laser kits even for elementary schools from $100 upwards. Next one, please. This is an example of pulse holography. The ruby laser is capable of emitting considerable energies of the order of 1 joule in 20 or 30 nanoseconds. And therefore it is possible to photograph moving objects. Now this is here the solution of a problem which would have been quite impossible before the laser and before holography. Because here is, for instance, the problem that we have got a jet issuing from a nozzle at a velocity of 2 Mach and say a temperature of 1500 centigrade. Now take photographs of the microscopic droplets in it. But all you have to do is to take a pulse laser, shine it through the jet, and then put a photographic plate behind it. Then afterwards you can reconstruct the object and simply go with the microscope right through the jet and see every droplet. This has been done here in Arizona. Next one, please. This is another application of the same principle, following mosquitoes in flight. On one hologram, you can take quite easily a complete picture of, say, about a yard of dirty water or of air full of mosquitoes. Next one, please. This is another application of pulse holography, a rather interesting one. It shows a bullet in flight. This experiment was first done by TRW in California. And when they took such a hologram, they saw to their surprise it wasn't just a picture of the bullet and its shock wave. It was an interferogram, because you see they saw all these fringes in it. Now what happened? It turned out that the laser, before the bullet came, gave a pulse. And that produced a plane wave in the undisturbed air. Now that plane wave was frozen into the emulsion. Afterwards, the holographic picture of the bullet was also frozen into the emulsion. The two were revived simultaneously, and these two light waves, which had never seen each other, interfered with one another, just as if they had been simultaneous. So this was the beginning of holographic interferometry, which interferometers with one branch only. Next one, please. Well, another application of holographic of pulsed lasers is that for portraits, for holographic portraits, because during the taking of a hologram, the object has not to move relatively to the reference beam more than about an eighth of a wavelength, or say a 10,000th of an inch. But as the pulse laser is capable of emitting sufficient energy for a photograph in 20 or 30 nanoseconds, so this may be possible to take holographic portraits. It's true only after devoting considerable work to the extension of the coherence length of the pulse laser. This is the author of the first portraits, Sieber of Conductron. Next one, please. Now this is here a portrait taken of myself, which was exhibited in Stockholm at the Nobel lecture. It shows me natural size and almost indistinguishable from the original, except that it doesn't talk. Another application of holography to vibrating systems. I said before that if the object moves an eighth of a wavelength, a quarter, then it's washed out. But then when it moves a full wavelength, then something is visible again, and so on. This here shows vibrations in terms of full wavelength of change, which is actually half a wavelength movement of the membrane. And it's a very complete illustration of vibration states. Next one. By the way, has a miracle happened or Oh, it isn't quite 6 yet, so fine. So a miracle hasn't happened. Yes, this is a guitar. Next one, please. This is here another application of holographic interferometry. It's a holographic picture has been taken of an object before and after a little compression. And then the two pictures of this, only very, very little different, will interfere with one another just as if they had been simultaneous. This is now one of the most important technical applications of holography. And I'm afraid I can only give you an acoustical picture of it, which is, well, it's used, for instance, in the testing of car tires. You take a holographic picture of a car tire when it has settled down. Then you blow a little hot air on it. Now, if the tire is perfect, then it will expand uniformly. But if there's a little cementing error in it, a very small flow, then a small blister will show above that spot. And the blister can be only a thousandth of an inch or even less. You can see perfectly well which a number of interference fringes, something like 10 interference fringes in it. Now this is one of the applications. Another, perhaps even more striking application is that for the honeycombs which are used in aeroplane wings. That's the honeycomb structure, and at the two sides there is aluminum foil welded on it. Now find out whether the welding is perfect or not. It's an almost impossible problem, but the first American firm which was founded in Italian holography, GCO Optronics in Ann Arbor, has made an enormous machine which weighing 12 tons, which a hologram is taken of that foil, and then a little hot air is blown on it. Afterwards, in the interference figure, you see if a single one of those millions of words is out or out. So this is a combination of holography with the wonderful discrimination power of the eye, which can really discover one irregularity in a million. Well, other industrial applications of holography are also known, but I cannot show the slides, and so I have to go. Well, try to explain as well as I can things acoustically. A very important idea was contributed to holography by a Soviet physicist, Yuri Denisyuk, in 1962, even a little before the holographic explosion. he had the idea of combining Lippmann's method of color photography with the idea of holography. What one has to do is to put the reference source and the object at two opposite sides of the plate. Then standing waves are produced between these two waves. And those standing waves produced in a fine emulsion precipitated silver granules, which practically don't absorb but scatter. And they are spaced, roughly speaking, half a wavelength from one another. That's if it were a very fine crystal. Now then, it's easy to see, it would be easy to see if I could show the picture, that those Lippmann layers will afterwards illuminate the reference beam, reflect exactly in the direction of the original object beam. What's more, in the original color, because by the spacing they sift out the original color. Only for the original color will the wavelets emitted by those Lippmann layers be again in phase and produce appreciable intensities. Now this then was the beginning of color holography, and also it's very important. These pictures had absolutely no second image, and second, they could be inspected and seen in white light. These are reflecting holograms. Now, I must say that the development is not yet very perfect. One can produce fairly good two-color holograms, but with three colors it's still not very perfect, and one of the things on which I'm working now is just to improve three-color holograms. Perhaps I can mention with a few words things on which I'm particularly interested now in holography. Well, one of the things I would like to do is to give the artists a new medium, holographic art. It's true that such a thing exists already in Nottingham here and in Detroit in America. There was already an exhibition of holographic art, but that's not what I mean. What I mean is that the artist shall really be able to use the third dimension without any restriction. Now the method to do this is not simple photography, because we cannot photograph a landscape in laser light. The intensity is not enough, the coherence length is not enough. But one can put a big lens before the hologram, which makes something which is at arm's length appear as if it were at infinity. Then the artist can model an object so that through seeing the lens it seems to extend to infinity, or at any rate to a very great distance. And then one takes a hologram, and looking into that it becomes a landscape. Now this is one of the things in which I'm interested, because I have a feeling that artists must be already a little fed up with the present very two-dimensional abstract art. Of course, there's no compulsion for them to be realistic in 3 dimensions. They can make 3-dimensional abstract art observation. Another thing in which I'm very interested is 3-dimensional cinematography. It's so happened that just before at the First Holography in 1947, I was working for several years in the British Thomson Houston Company on stereoscopic cinematography, until I realized that no perfect solution could be found by orthodox means. Not for large theaters like this one. One can make it quite well for small theaters, so almost up to the length of 10 meters, but not for a room like this. The reason is, well, there are several reasons. One of the reasons is this, that if you make such a screen with lenticules or little mirrors or prisms, then if the mirrors are small enough not to be resolved from the first row, then they diffract too much in the last row, and vice versa. So it was impossible. In 1966, I realized to my great surprise that holography had also solved this insoluble problem, because a hologram is invisible in itself. It can contain a terrific superposition of optical elements. This is one of its advantages. And one can indeed solve the problem of cinematography without Polaroids and other viewing aids, because the hologram is, so to say, an astonishing generalized optical system. Well, take an ordinary optical system such as a lens that can produce out of a point source the image of it, a point image of it. But as you have seen before, a hologram can produce out of a point source, for instance, a three-dimensional image of Abraham Lincoln. So it can solve also that problem that a point source, a projector, simplified as a point source, shall be visible, the image produced by that on a large screen shall be visible only in certain strips in the audience where left eyes can be placed, and then a second projector where right eyes can be placed. It's a bit difficult to explain, especially without a picture, so I just leave it at that it's theoretically possible, but the realization will take quite a lot of time and money. Now, perhaps I'll talk of things which were not foreseen in this lecture, but which can be perhaps explained a little better without pictures. I have not mentioned quite a few applications of holography. One of these is, for instance, translation. What the hologram did there, in the examples you have seen, was translating a picture point into a reference point into some complicated object. But this is a special case. One can generalize it. One can make can take two pictures A and B so that A will evoke B and vice versa. One can do this in very considerable generality. For instance, my students have translated Chinese ideograms into the equivalent English sentence. And Professor Butters and Mike Wall in Loughborough University have recently constructed holograms which reconstruct the portrait of somebody from his signature and vice versa. These can be, of course, used commercially. And, of course, holographic signatures, holographic portraits, etc. have been already produced, and holographic vouchers are already in circulation in the United States on a small scale. Cryptography, of course, is a colossal field open for cryptography, because all you have to do is to take a hologram through a diffusing glass. Then you will never be able to reconstruct a hologram unless you have the same diffusing glass or a precise replica at your disposal. It's curiously enough, this is not secret enough for the military. Now, perhaps I'll talk of something else which was not foreseen in the lecture, and this is acoustical holography. The idea of acoustical holography arose very naturally because the principle of holography is, of course, applicable for any sort of wave motion. In acoustics, coherence is absolutely, there's absolutely no difficulty with coherence. Sound sources can be made to emit perfectly regular sinusoidal oscillations, and there's no difficulty with coherence. The difficulty is rather with the equivalent of a photographic plate, because the photographic plate is a wonderful thing. It contains, small size, say 100 million of independent quadratic elements, each of which will respond to the intensity. It needn't be exactly quadratic, some function of the intensity. But if you want to do this in acoustics, then the possibilities are very limited. The most sensitive method is to take microphones or hydrophones. but just try to make a million hydrophones, so it will cost a little too much. Besides, so far the top achievement in this line is 100 by 100 matrix of hydrophones made by the Bendix company in America, and even that is a rather difficult achievement. Even that doesn't give what one would expect. It does not give a 100 by 100 picture, but something like a 10 by 10 picture. Now I must explain the reason. It's laser speckle, or one could rather call it coherent speckle. Anybody has ever seen laser light is struck how disagreeable it is, because a sheet of white paper looks like they're crawling with ants. Now the crawling is put into it by the restless eye, but the roughness is really there, it's objective. And it's not the fault of the laser light. The laser light transmits information, but information which we don't want. We are so used to incoherent light that we are not interested in the microscopic dimples and projections of a white sheet, which are just of the order of wavelength, and which therefore scatter light, and the scattered wavelets then recombine, the wave vectors recombine in space, and can produce a very high maximum or a very small minimum, and on the whole a colossal noise-like phenomenon. The rule for this is extremely simple. It can be quite generally stated. If you want a signal to noise level 20 dB in a hologram, then you must spoil the definition by a factor of 10. If you want a 40 dB signal to noise ratio, you must spoil it by 2 orders of magnitude. This is a fundamental difficulty in the case of rough objects. There is a holographic microscope has been sent, for instance, to the moon to take pictures of undisturbed moon dust. And of course this is a rough object. So for the time being they've helped themselves by taking 4 different holograms and then copying the pictures of one another. So it's averaging 4 to 1. But of course it will reduce the error only by a factor of 2. Now, in the case of rough objects, there is really nothing much one can do against this. And that's not so bad in light holography, because there we have got definition to throw away. A hologram such as you've seen before really has got a diffraction definition of the order of a wavelength. Thus the eye cannot see less than about 100 wavelengths, so it can throw away a factor of 100 without efficiency. But in the case of sound holography, this is difficult, because sound waves cannot be made all that short, nor can we multiply the receiving elements quite so much. So the speckle there is rather serious. Now, I hope nevertheless it will be overcome, because sound holography, after some difficult starts, is really making progress. Last summer I visited the Holosonics company, that again is an American company formed on holography and sound holography. It's founded by the inventors, Dr. Brennan and Mr. Neese, and after about 5 years of work, they produced some very nice sound holograms. They had to use interesting tricks to get it good. It took them all this time. The chief trick is that these are focused holograms, and so the object must not be very far from the plane of the receiving surface. The receiving surface is simply a liquid surface. Yeah, imagine that it's a water surface. The object, say a hand or an arm, is dipped into water, and then an acoustic lens makes an image of it on the water surface. Now it's a general belief even among acousticians that acoustic lenses are very bad lenses. It's curious how long I shared this belief myself for many years, but just not true, because there are liquids with a velocity of sound about half that of half that of water, and that gives a refractive index of 2. Now if you have got a refractive index of 2, then for an f4 lens you need such a small curvature that the spherical aberration, astigmatism, other errors become quite small. So it's quite remarkable what a good f4 lens the holosonics people have produced with this liquid. And by the other trick, by the focusing holography, the picture is not sensitive to disturbances. It's separated anyway by the lens from the tank. You can splash about in it and the picture remains remarkably steady. Now, what is disturbing in these pictures is what they would call spatial speckle. You see, you can focus one plane on the water surface, but the other planes will not just appear behind it. They will produce speckle in that plane by the interference of the wavelets, sound wavelets, which will interfere in the focus plane. And that's, for the time being, the disturbing phenomenon. Sound holography, in principle, offers something very, very promising, and it is the early diagnosis of soft tumors. Sonography, sonar methods in medicine are already well known. And it's shown that they can show up very small and very young soft tumors. Now, holography for the time being still suffers under the difficulty that if you take, for instance, a hologram of the breast, then it will look, there's too much detail. The speckle suppresses the object. That, however, I can see that there are methods of overcoming it, and from the point of view of medical applications, I think this will be far the most important. Another is, of course, holography in the case of pregnancies, because nobody has really good conscience about using X-rays. In particular, not in the case of pregnancies. Ordinary pregnancies, they don't take any X radiograms. But ultrasound is perfectly harmless below a certain intensity, which is so high that we needn't worry about it. So this is also a very promising thing, the application of sound holography in obstetrics. Now, I'm afraid a lecture on holography, which are pictures, is very much less than a lecture, and I'm afraid I'll have to break it off now, expressing my deep regrets that I could not show the more than half of the pictures we have prepared for you. Thank you.
Professor Cherry will propose a vote of thanks. Will you come up here, please?
Rector, Professor Gabor, ladies and gentlemen, I feel a little embarrassed at being asked to offer this vote of thanks in view of the so many distinguished people here. I think my only excuse is that I've known Professor Gabor, I could say longer, if not at least as long as anybody in this college, having been a fresher with him in 1946 or 7 when we both came to college at the invitation of the late Lord Jackson. I would like to say that my one great regret tonight is that Lord Jackson is not with us. I can't help but think how proud he would feel if he could be here on this occasion. Dennis Gabor has brought great honor on this college and, of course, on our department. It's not often that the Nobel Prize for Physics goes to an engineer, for an engineering product, of an inventor. And our department has brought great honor upon us. We can't help feeling bathed in its reflection. Well, I won't take up your time at all after such a magnificent and fascinating lecture on this great occasion in the history of the college, except I'd like to thank you, Professor Gabor, for this fascinating lecture you've been given us tonight on behalf of all of us. We've been delighted to hear, in spite of all the appalling technological difficulties that have surrounded you tonight, this address originally given in Stockholm. Thank you very much indeed, sir.